3-6, proportional and non-proportional relationship. Inductive reasoning is when you use a pattern to find a general rule. If the relationship between the domain and range of a relation is linear, then the relationship is described as a linear function. And we've previously learned a lot of this in the beginning chapter, earlier in the chapter. If the equation is in the form of y equals kx, then the relationship is proportional. All proportional relationship graphs have to pass through 0, 0. So if you have the example y equals 3x, it is written in the correct form, so you would be able to say that it is proportional. And then if you used values to replace x and solved for y, your graph would look a lot like this one, where it is crossing through the 0, 0. So, with proportional relationships, there's a couple of things that you have to do. Once you have your set of data, then you want to first graph the data. So, a lot of times they will give you a chart that has numbers on it with values. You want to graph those values. So you have to figure out which one is your independent and which one is your dependent, and then you want to graph them. From there, you want to write an equation that describes the relationship. The relationship from your x and your relationship to your y and how those relate to each other. And then you want to use that equation to predict another value. So in some of the equations you'll see, you will figure out the equation, and then it may ask, use the equation to predict how much money will be donated in 4 goals, or 5 goals, or 8 laps. So they'll give you an example. So let's take a look at this example. A professional soccer team is donating a certain amount of money to a local charity for each goal they score during the regular season. So they've given us the table that shows the number of goals, 1, 2, 3, 4, 5, and so on, and the money that they raise for each goal, or that they're going to donate. So you first want to graph the set of data so that you can see the relationship that's happening. So if they have one goal, they raise $75. If they have 2 goals, they raise $150. We have 3 goals at $225. 4 goals at $300. And mine's going to be a little bit off just because I'm freehanding it. I would suggest that you use graph paper when using these. Okay, so this is approximately what our graph is going to look like. So we've now graphed it. Again, mine is a little bit off. This one should actually be passing through this 0, 0. There you go. It should be more like this, but because I'm freehanding it, it's a little off. So this is considered a linear equation because it is passing through the origin, so it is linear. So now you want to write an equation that describes what is happening. So for every goal that they are making, they are donating $75. So for 1 goal, it's 75. For 2, it's 150. For 3, so the dollar amount, so D, is $75 times whatever the goal is. So then it may say, use the equation to predict how much money will be donated after 12 goals. So if we wanted to replace this number with 12, we could solve here, because we would just do 75 and multiply it by 12. So if you do 75 times 12, you get 900. So that means that they would raise $900 if they scored 12 goals in a regular season. When the ratio of the value of x and y for select ordered pairs are different, the equation is not linear. So if you wrote a fraction for the first set of ordered pairs, it would be 1/9. The second set is 2/12. Those are not equal to each other. The next one is 3/15, which again is not equal, and 4/18, which is not equal. So you can see here that the ratio of each of these are not equal to each other, making it non-linear. So now we're going to look at how we can write an equation for this particular set of data. So you want to look to see what is the pattern that is happening amongst the numbers. So 9 to 12 is plus 3, 12 to 15 is plus 3, and 15 to 18 is plus 3. The relationship with x's is it's just plus 1 each time. So we have to determine, well, what is happening to x to get y? So in this case, y equals, if we do 3 times x, that just gives us 3. But if we add 6, then that would give us 3 times 1 is 3 plus 6 is 9. And so you can try that equation to see if it worked, and you can test it out for all of the numbers. And once it works and you notice that that is an equation that is true, then you would say that that is the equation for that set of data. Pause the video to take a look at this example. Write an equation in function notation. Remember, function notation is, instead of writing y, you just write fx. So the function telling me what you're doing with the numbers to get that specific answer for the relation shown in the table. So, looking at this particular set of information, you want to look at the relationship that is happening between the x and the y. So, if we have 1, what's happening to 1 to get 3? Well, if we have 1 and we're getting 3, we would be able to say, well, we're adding 2. So we could possibly make that our pattern. But then 2 to 2, we don't add 2. So we go back to our original where we have 1 to 3. So we have the option here of making the x negative. So maybe if we said negative x, so if that was negative 1, what do we do to negative 1 to get 3? We add 4. So let's try that for 2. If we have negative 2 and we're trying to get to positive 2, we add 4. So it works for the first two. If we have negative 3 and we add a positive 4, we get 1. So it works. And if we have negative 4, we add 4 and we get 0. So since it works for all the values, you would be able to say that is your equation for that particular relation. So let's pause the video and write an equation in function notation for the graph. Remember, function notation is the fx. You want to select some points along the graph, put them in a table, and find the relation. So let's go ahead and pick 3 points. You should always try to pick points that intersect at specific lines. It just makes it a little bit easier for the math. So our first point is at x 3, y 2. The next point is x 2, y 0. Then we have x 1, y negative 2, and then you have x 0, y negative 4. So if you're looking at this equation, or this set of data to create an equation, you want to find what is happening to x to get y. So for the first example, you're subtracting 1. The second example, you're subtracting 2. The next example, subtracting 3. So that doesn't work. So let's begin with multiplication. If you multiply 1 times any number, you still get that number. So we're not going to start with 1, but let's maybe do 2. So 2 times x would be 6. I would have to then subtract 4 to get 2. 2 times 2 would be 4. I subtract 4, I get 0. 2 times 1 would be 2. I subtract 4, I get negative 2. 2 times 0 would be 0. I subtract 4, I get negative 4. So my fx, or my function notation for the graph, would be 2x minus 4.